Okay, so now you can see this. Okay, hi everyone. Okay, this is in this lecture we're gonna talk about linear regression. Also, we are gonna, if I think we have time, we'll cover LDA and QDA. So also note that I assume all of you have watched the video on regularization and overfitting. Have you? Except you watched that, please. Have you watched that? Yeah, because some concepts, guys, please, some concepts in that session, in that video that I recorded and put on video on YouTube, those will be used in this session. Okay, if you haven't watched, please watch. And whoever is watching on YouTube, if you haven't, pause now and go and watch it and come back. Okay, so let's go over linear regression. So what was regression? Do you remember? Regression was predicting some labels, and the labels could be continuous, right? In contrast to classification, where the labels were discrete. Okay, so, and we can have either linear regression or nonlinear regression. So nonlinear regression is more complicated. It has more complexity to learn the pattern of data, but linear regression fits a line to data. We have different algorithms for linear regression, at least 3, and there are simple linear regression, ridge linear regression, and lasso linear regression, all of which you can find their libraries in scikit-learn as well. Okay, so first, let's talk about linear regression. Whenever you have any question, please feel free to ask, okay? Interrupt me. So consider a data set x1 to xn, where xi is the ith point. It's a vector in d-dimensional Euclidean space. So it's a d-dimensional vector, okay? We have some labels to y1 to yn. So we have n points. The points are d-dimensional, but they also have labels y1 to yn, where yi is a label for the ith point, and that label can be p-dimensional. Usually p is 1. Usually the labels are scalar. However, we might have vector labels. Some examples, for example, hi. So for example, your data is, I don't know, I think here we have, can be weather, temperature. So these are the elements of X. So weather, temperature is a scalar, longitude, latitude, etc. If you put them together, you will have a d-dimensional vector. For example, if you put these 3 together, d will be 3, right? And your label can be the pollution of the city, which is a scalar. However, you might have a second output too, label. For example, pollution of the city and I don't know, what do we say? The rate of immigration, something like that. So you will get these 3 as input, you'll output 2 things, for example. And then in that example, D will be 3 and P will be 2. But if it's only pollution of the city as the output, P will be 1. So I think it's obvious. The labels are not necessarily discrete. They can be continuous, right? Okay. Now we consider a map F. So do you remember we said that when we are learning machine learning model, that's a map. So which maps input to some output for our task. Whether we want to do classification, regression, some embedding, and these things. So it maps. You can see it as a map. And now we consider some map which maps the data to the labels. So maps data to the labels, right? And you can see labels as that true map, which you don't have, plus some noise. I think you saw similar thing in the lecture of regularization and overfitting, right? Okay, and epsilon also is p-dimensional, because why is p-dimensional? If p is 1, then epsilon is a scalar, and epsilon is a noise. Okay, now in regression, we want to estimate this map, map F. We want to estimate. In linear regression, we want to estimate this map by a line. When we say linear regression, then we want to estimate it by a line. When it's nonlinear regression, it can be any nonlinear function, right? What do I mean by a line? Consider a bunch of data points, a cloud of data points, okay? When I say I fit a line to it, I regress a line to it, it means that a line which has least amount of error passes through this cloud with least amount of error, right? By the way, when I say line in multidimensional space, it's hyperplane, right? So in 2D, it's line. In 3D, it's a plane. In 4D, in 5D, you can't visualize it, you need to imagine it. It's a hyperplane, okay? So, and when we say affine function, so either a line or affine, what's the difference between line or linear model, linear function and affine function? Once we talked about it, so linear function is like this, it has a slope, but affine function has a slope, but it might have some intercept or bias, right? In the literature, sometimes they call affine function linear function too. However, to be more precise, linear doesn't have any bias. However, we use them interchangeably. Okay, first, consider the case where P is 1, when the dimensionality of label is 1, okay? Then what would we have? So f of x, the map that we are gonna estimate, is one-dimensional. It's a scalar because P is 1, okay? And then we have beta 0 and beta j. So we have several betas, beta 0, beta 1, until beta d. So here, beta 0, beta 1, beta 2, until beta d, each of which is a scalar. See, I have said it here. Each of which is a scalar, right? And let xj be the jth element of x. Okay, so the vector x is x1 until xd transpose. Why do we have transpose? Because we consider the vectors to be column vector, right? Okay, now why are we introducing beta? Because these are the learnable parameters. So these function that we are estimating, whatever we do in machine learning, we have some learnable parameters. We have two sets of parameters usually in machine learning: learnable parameters and hyperparameters. Learnable parameters are learned by optimization. Hyperparameters are set or chosen by the user. And which hyperparameter we should use? Using cross-validation. That I assume you have watched the lecture of regularization and overfitting. In that lecture, I talked about cross-validation, how we should choose the best hyperparameters, okay? If you have any question regarding that, please ask me. So we have some learnable parameters here. There are d plus 1. And why do I have beta 0? So why do I have beta 0, beta 1 to beta d, while I have only x1 to xd? Because I want to learn the bias. If you have been in the deep learning course, even in the perceptron and other simple neural networks that we discussed, we also want to learn the intercept or bias. So whenever you are fitting something to the data, you need to take care of the bias. Otherwise, what happens? Assume your cloud of data is like this. Then even if you don't have any bias in your model, that would be fine. However, consider the case where this is your cloud of data. And if you fit a line to that, it would be like this, because it has to pass through the origin, and it would be awful. But if you had introduced bias, then it would fit something like this, right? So you need to take care of the bias or the DC signal, whatever you call it. So these are the learnable parameters, and beta 0 is specifically for learning the bias or intercept. And as you see, we are having a linear combination of the elements of X. Why? Because we are fitting a line. This is linear, right? We don't have any xj squared or any nonlinear function of xj. So we have only scalars times the elements. So this is linear function. Okay. One way to do this estimation is to minimize the least squares error. So I have labels, I have yi's, I have xi. So this is my data set, right? I have pairs of xi, yi. I goes from 1 to n, right? Xi is d-dimensional, yi is p-dimensional. Here, we assume that p is 1 for now, okay? And so we feed xi to f. It outputs f of xi. It needs to be close to the label, to the desired label, right? Therefore, we can minimize the error between them. So f of xi can mimic what lyi is, the behavior of the labels, right? So that's the thing. And what this is called least squares error. Why? Because of this minus, this is error. This is a squared, right? Least is, and what is least? Minimization. So least a square error, minimization a square error, right? Between the labels and the estimated model. Okay, sure. And we have summation over the points. I goes from 1 to n, right? Okay, now what did we have in equation 2 in the previous slide as the, we had it as the definition of f of xi, right? Equation 2, f of xi. So what is it? Here it is. F of xi is beta 0 plus j goes, sigma j goes from 1 to d beta j xj. By the way, one thing in parentheses, we can simplify it if we consider x0 to be 1, as we also had it in perceptron in deep learning course. You can have summation j goes from 0 to d beta j xj if you define x0 to be 1. Okay. And so we have something like this. So I replace f of xi with equation 2 with its definition that we talked about, is linear estimation. And I will have this minus beta 0 minus summation of beta j xij. And what is xij? Xij. So because if you remember in equation 2, we only had xj. Why? Because I was assuming I only have 1 point, x. And xj was the jth element of x. However, now that I have summation over the points, I have x1 to xn, each of which is a vector, right? Therefore, xij is the jth element of the vector xi. Do you get it? So when I have an underline under it, I mean it's bold, it's a vector, okay? x1 until xn, each of them is a vector, d-dimensional vector. So for example, the x1 will be x11, x12 until x1d transpose. So xn will be xn1 and xn2 until xnd transpose. Therefore, let xij be the jth element of xi. Therefore, xij is the scalar, right? Also have beta j here as before. So the only difference between equation 3 and equation 2 here is that xj became xij. Okay. Now I also have written it here. So consider equation 3. This is our optimization. What are the optimization variables which we want to find? These are the Lerner parameters, right? Beta j goes from 0 to d, right? Now we can write it in matrix form because it's easier to work with matrices maybe. Okay. Let beta be a vector of beta 0 to beta d transpose, right? It's a column vector. So it's d plus 1 dimensional. Clear? Okay. Now x. I define capital X, which is a matrix. It's a matrix, right? To be n by d plus 1 dimensional. Therefore, it has n rows, d plus 1 columns. And what am I doing? So I'm putting, this is x1 vector. So it's the first point. This is the second point, x2, until this is xn. By the way, as these are row-wise, I need to transpose them, right? Because x1, x2, until these vectors are column vectors. In order to make them row-wise, I will have x1 transpose, as you see it here, x2 transpose, xn transpose. I also put a column of ones at the start just for the sake of bias, corresponding to beta 0. So x1, 1, x2, 1 until xn 1 correspond to beta 1. Or x1d, x2, 2d until xnd, they correspond to beta d. And the ones at the start, they correspond to beta 0. Okay. Therefore, this is the matrix X, right? So X has the data, X's, including ones for the bias. And Y is also, we have Y0 until Yn transpose. Sorry, it should be Y1. I apologize. So that was a typo. Y1 until Yn transpose, okay? Which is n dimensional. Because we have n points, each of which has a label. And I assumed for now, labels are scalars. Therefore, I can put them in a vector, will be n dimensional, right? For now, I have assumed y1 to yn, each of which is a scalar. Okay, the above optimization problem then becomes this. So equation 3 becomes equation 4. Why? Let's take a look at that. So I have yi here. I replace it with the vector y. Also have kind of brought beta 0 into the summation using the technique that I talked to you. So it will be summation of beta j xij, j goes from 0 to d. And I assumed xi0 is 1. So, and you can see xij as the matrix X. So again, the first column, I assumed it's 1. So X, and also I have betas, and as you see, they are multiplied to each other. Therefore, I have x beta. But how do I know whether I should put beta x or x beta? Just the dimensionalities should match. Y is n by 1. It's a column vector, n by 1. What is x? N by d plus 1. And what is beta? D plus 1 by 1. So they match. You can't have beta x because they don't match in the multiplication. The dimensionalities don't match. Okay, that's correct. So, and as you see, as I have, by the way, as I have a squared here, this is squared. You can see it, summation of a squared. So you can see it as L2 norm. There is no square root. There is no square root over the summation. Therefore, it's a squared L2 norm. Okay, so far clear? And the optimization variable became the vector beta, right? Rather than beta j scalars. Okay, now the cost function can be simplified. How? Using that famous formula. Something, L2 norm of something squared becomes something transpose something. So L2 norm of x squared, you remember that was the formula that we had. This is a quadratic form. in the recall preliminaries. Okay, now I can see it as one thing. So it becomes this transpose itself, right? And now I apply this transpose into the elements of the parenthesis. So this will be Y transpose, but applying on X beta, it changes the order. So it becomes beta transpose X transpose. And I still have this term. Okay, now let's multiply the terms to each other. So the first one, Y transpose Y, I have it here. Then Y transpose X beta with minus. Then beta transpose X transpose Y. By the way, this should be a small y. And this is beta transpose X beta, but with plus. Why? Because we have two minuses. Right? Okay. Now let's take derivative with respect to beta. Right? Yeah. Because why do we do that? First order optimality condition in optimization, or whatever we learned in high school. It's an unconstrained optimization problem. Take derivative, set it to 0. Right? So take derivative, we take derivative. The first term is a constant with respect to beta. Its derivative is 0. The second term, what is it? Its derivative is X transpose Y. You say no, you can use the technique that we discussed in this course, the fake dimensionality technique. And you will see that it's X transpose Y. It's not Y transpose X, just because of the fake dimensionality technique that we discussed. Or you can say beta, again, fake dimensionality is 5 by 10, for example. Then this needs to be 10 by 5. Assume. But this, as it is vector, it's 5 by 1. So this will be 1 by 5, doesn't matter. And when you take derivative with respect to beta, the derivative also needs to be 5 by 1. Therefore, you need to have X transpose Y, not Y transpose X, because Y transpose X is 1 by 5. I'm using the fake dimensionality technique, okay? So here, and then also, so, the derivative of this with respect to beta is this. Then this also, its derivative becomes X transpose Y. So we have two of them. So this is corresponding to this, and this is corresponding to this, the derivatives, okay? And now this one. So this is actually quadratic with respect to beta. So the fourth term is quadratic. Therefore, we'll have two X transpose X beta, okay? Set it to 0. And as you see, this 0 is a vector of 0. Why? Because the derivative is a vector now, okay? So bring these two, by the way, these two become minus 2X transpose Y, right? Bring this to the right hand side. You will have this. These two, the twos in the left and right hand sides cancel each other, right? Now I left multiply the sides by X transpose X inverse in order to cancel this out. Okay? Do you get it? Right? So this goes away. Then I will have X transpose X inverse. And also I had X transpose Y here. Right? So what is this? This is actually the formula of linear regression. This is the formula. Okay? And we just proved that. This is the formula. Whenever you say beta, usually you can see it in the internal also. X transpose X inverse X transpose Y. If one thing is important here, this is true if you consider X's to be row-wise. Recall what we did. Here, we put X's row-wise. Okay? If you put X's column-wise, then some transposes change in this formula. Okay? That's one thing. And then, so you have found the learnable parameters, you learn the parameters. So you have X's, right? This is your data. You have Y, the training labels. So you have it. You have fitted the line. These are the parameters of the line, right? You can see it as the slope of the line, or the slope of the, or the normal vector of the hyperplane. You can see it as a normal vector of the hyperplane. What is normal vector? The vector which is perpendicular to the hyperplane. Okay. In the test phase, assume some new x's come. You don't have y's, you need to predict that. You want to regress, right? What do? So these are, you can still form the matrix X for the new data using the same equation that we have here. So you have new points. Assume in your test data set you have q points. Okay. Then your new X will be q by d plus 1 dimensional. Right? You put them, you stack them row-wise next to each other, and you will also consider the bias 1. So you'll have q rows, q test points, and d plus 1 dimensional. So you will have some x, and then you multiply it by beta. Why? Where did this come from? Y equals x beta. Because I want you to know the reason of everything. Don't memorize anything. Why? Because we just minimized that. The distance between y and x and beta. Therefore, y needs to be as close as possible to x beta. So in the test phase, we use y equals x beta. Okay. Now, this is x, and this is the beta that we just found. Okay. By the way, this x can be the x of training too. Sometimes you fit the data, you fit the line on the training data. You also want to regress the training data as well, right? In scikit-learn encoding language, so what we did here is fit. This is transform. There is a function also fit transform, fit underscore transform, which does the operations both. So it fits and then transforms. Then in fit transform, this x will be the training data again, right? Because it fits on the training data and it transforms on the training data again. But you can also have a transform function which transforms on the test data. So this x is either training or test. Okay. Now we talked about the case where p was 1, right? We assumed that the labels are scalars. Now let's make it more complicated. What if we have 2 or multiple outputs, multiple labels, pollution of the city and the immigration rates, maybe something like that. So p might be more than 1. Then we need to consider. So y here, the labels now are n by p. Previously they were n by 1, was a vector. Now y, the labels become a matrix because we have n labels, each of which is p-dimensional now. Assume I put them row-wise. Again, I understand that. I always told you in this course, I usually consider the vectors row-wise. Column-wise. In regression, this is an exception. People like to put them row-wise, okay? That's why you can see always I'm putting transpose. So this is y1 transpose, a vector, row-wise vector. Then y2 transpose until yn transpose, okay? Then it will be n by p, n rows and p columns. And it's capital because it's a matrix. Then betas also will be a matrix. Previously they were a vector. Beta will be d plus 1 by p. Previously it was d plus 1 by 1, right? It was a vector. So here, as you see, yes, give me a second. Yes, so we will have a d plus 1 by p parameters. So you can see a vector b, d plus 1 by p, each of which these elements we should learn. We should learn this matrix for the sake of regression, okay? Now, beta j is also, you can consider beta j p-dimensional. What does it mean? Yeah, if you put beta j p-dimensional in this, you'll see that it is d plus 1 by p, doesn't matter. And yj is p-dimensional, okay? So in other words, when p was 1, we had beta j was a scalar, yj was also a scalar. Now that p is not necessarily 1, beta j is p-dimensional, yj is also p-dimensional. So betas correspond to the labels, because we want to regress the labels, predict the labels. Now the optimization problem. Let's go back to our optimization problem. What was it beforehand? Equation 4, recall it. Minimize squared L2 normal, y minus x beta. Y was a vector, x was a matrix, beta was a vector. Y was n by 1, x was n by d plus 1, beta was d plus 1 by 1. Now that we have p labels, x, we don't change x. X is the same as before. Okay. However, y and beta, they have become matrices, y and b, right? L2 norm becomes Frobenius norm because of the matrix. Okay. Recall preliminaries. So we'll have a squared Frobenius norm, y minus xb. B is a matrix of betas, right? Now let's simplify the cost function. The squared Frobenius norm. Again, do you remember this formula, the quadratic one? We had trace for it. X transpose X, right? Therefore, we have trace here. This transpose this. Apply this transpose to the elements of the parentheses. We'll have Y transpose. The order is changed. Beta B transpose X transpose. We have it the same as before. Then trace is a linear operator. It can be applied on each element. Also multiply the terms at the same time. So I have trace of Y transpose Y minus trace of Y transpose X beta minus trace of beta transpose X transpose Y plus trace of B transpose X transpose XB. Okay. Now let's take derivative, set it to 0 as before. By the way, this 0 is the matrix of zeros now, because the derivative is a matrix, right? This element, the first term, is a constant with respect to B. Our optimization variable is B now. So it goes away. The second one is derivative with respect to B. It's a linear function with respect to B. It will be minus X transpose Y. Why isn't it Y transpose X? Use the fake dimensionality technique, which we discussed before. The third term, take derivative with respect to B. It will be X transpose Y. The fourth term is quadratic with respect to B, right? You will have 2X transpose XB. Set it to 0, matrix of zeros. Then these two become minus 2X transpose Y. You bring it to the right-hand side. So we'll have 2X transpose Y. Here we also have 2X transpose XB. These two 2's cancel each other. Then I left multiply the sides by X transpose X inverse in order to get rid of the X transpose X in the left-hand side. So this goes away here. Then we'll have X transpose X inverse, X transpose Y. Again, this is the formula for the linear regression, but for multiple labels. As you see, it's very similar to the formula of regression for one label. This is just a generalization to that, to higher dimensional labels. Again, we were minimizing the difference between Y and X beta, XB. Therefore, in the test phase, in the transform, we'll have Y equals XB, right? So here, this is X, and this is the B that we found. So we can use it either for transforming training or test data. So we have fit a line. We have fitted the line. Now, this was simple linear regression, over. So we fit the line, simple. Now, ridge linear regression. So, what's the idea behind ridge and lasso linear regression? They are just regularized optimization for linear regression. So they are just regularizing. Again, recall the lecture that you watched, the 3-hour session that you watched about regularization and overfitting. We talked about L2 norm regularization and L1 norm regularization. If you regularize linear regression with L2 norm, it's called ridge linear regression, ridge regression. If you regularize the cost of linear regression with L1 norm regularization, with L1 norm, then it will be lasso linear regression, both of which exist in scikit-learn. Lasso regression, ridge regression. Okay. Why do we regularize? For various reasons. We talked about that in that session. For example, we want to avoid overfitting, right? Okay, so let's add L2 norm regularization term as a penalty, because regularization term, you can see it as a penalty, right? On the size of the learnable parameters. You don't want your learnable parameters, your betas or your b's to explode. You want them to be small, because especially in your computer, the numbers shouldn't get very big. So you need to penalize it. Now, again, consider the case p equals 1, where labels are scalars, okay? Then what was the optimization beforehand? It was like this, only this, right? Summation of I goes from 1 to n, yi minus beta 0 minus summation of j goes from 1 to d, all the dimensions, beta j xij, where xij is the jth element of the vector xi. You remember? We had it. Now I'm adding this penalty term or regularization term, which is L2 norm. Why? It is a squared L2 norm. What is L2 norm of beta, vector beta? Recall preliminaries. It's just this summation of j goes from 1 to d, beta j squared. This is L2 norm. We don't have square root anymore, so it's squared L2 norm, right? Again, as I can write it in the matrix or vector form. So we had it before. Now this will be lambda second lambda height squared L2 norm of beta. What is lambda, by the way? What is lambda? This is the regularization parameter. What does it do? By the way, lambda should be positive. Should be positive. Why? If it is negative, minimization of minus negative term, it means that you are maximizing. Do we want betas to explode? If you set minus lambda to be negative, betas will explode, become infinite. We want them to be small. Lambda needs to be positive. Also not 0. Why? Because we want to have the regularization term. It's regularization parameter which weights how much we want to care about the penalty compared to the actual cost function, right? It weights the regularization term. It's a hyperparameter again. It's a hyperparameter set by the user. You can find the best value for it by cross-validation. So we have this. Let's simplify it. We already simplified this term in the previous slides. The only thing which needs to be simplified is the regularization term. We have lambda squared L2 norm of beta. Therefore, it's lambda beta transpose beta, right? This is quadratic form. Now, take derivative of this cost function with respect to beta, which is the optimization variable, and then set it to 0. First order optimality condition. Okay, let's do it. Let's do it. As you see, it is becoming easy because it's becoming repetitive. But the more you see that, the easier it becomes, okay? This is constant with respect to, no, you will not be bored because L1 norm will be harder. So, okay, you will not be bored. So just bear with me. The first term is constant with respect to beta. Its derivative is 0. The second term, its derivative with respect to beta is x transpose y. The third term is also linear with its derivative is x transpose y. The fourth term is quadratic. It becomes 2x transpose x beta. The fifth term, which is newly added, becomes 2 lambda beta. Why? Because it's also quadratic with respect to beta. Set it to the vector of zeros. Okay? Now, these two can become minus 2x transpose y. You bring this to the right-hand side, you will have this. 2x transpose y. You also had this as before, but this is newly added, 2 lambda beta. Okay, now, let factor out 2, which is a scalar, we'll have this. Right factor out beta. Why? Because it's a vector, it's important whether you left factor out or right factor. So right factor out beta, because these two terms both have beta. And in the middle, you will have x transpose x plus lambda I. Why not lambda? Because this needs to be a matrix. Lambda is a scalar. When you factor out, it's like 2 lambda I beta. I is the identity matrix. You can write 2 lambda beta as 2 lambda I beta, right? Because I in multiplication doesn't do anything. Then you also have this. These two 2's cancel each other. Then we have a pen in the neck term here. In order to get rid of this, let's left multiply the sides by its inverse. So you will have this. This is the formula for the ridge regression where labels are scalars. As you see, it's very similar to the formula for linear regression, not regular linear regression. What's the difference? What's the difference? Plus lambda I. Plus lambda I, exactly, which is for the penalty term inside the inverse, right? Inside the inverse.
How does that affect them?
Okay, we'll see. So one thing, without looking at it, you tell me, when you are adding, well, let me write it down. So x transpose x plus lambda I inverse. Sorry, I'm not memorizing it. X transpose y. Okay? Yeah. You tell me. So compare it to x transpose x inverse x transpose y. In terms of linear algebra first, let's talk about it. What's the difference in terms of linear algebra? Lambda.
Addition.
What?
Addition of lambda.
Yeah, lambda we have it, and we know it's positive. It's not negative. It's not 0. There is a difference in terms of linear algebra between these. Of course, what you are taking inverse of, you're adding lambda I. What is lambda I? Let's write it down. So it's something like this. A diagonal matrix whose diagonal elements are lambda, 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 lambda until n, right? And the rest is 0. When you add such matrix to x transpose x, what are you doing? Yeah, exactly. You're strengthening or you're adding to the main diagonal. It's called you're making it more stronger, right? You're strengthening that. Why? Because all lambdas are positive. When you do that in linear algebra, what is it doing? So you have some matrix, you strengthen its main diagonal. If that matrix was singular, it becomes full rank. So in order, I don't know if you have coded with matrices or not. Sometimes in your code, when you run your code, it throws some error, or at least gives you some warning saying that your matrices are singular. If they're actually singular, it will be error. If they're close to singular, they will give you a warning. If you have coded with MATLAB or Python, whatever, you have seen that. MATLAB throws these warnings a lot. So what does it mean? It means that you can't take inverse of this matrix, right? It means that some of the eigenvalues might be 0, right? If the matrix is not full rank, you can't take inverse. It needs to be full rank. It's rank. Rank is something, rank of matrix. For more information, take a look at linear algebra, okay? So when you strengthen the main diagonal of matrix, you're making it full rank. So that's one thing that ridge regression does. But can we increase lambda to whatever we want? Let lambda be 1 million. First off, in the optimization problem, if you set lambda to be a huge number, the actual cost function goes away. It means that you are not fitting a line anymore. Okay? It even forgets what you were doing. It only penalizes. Okay? Therefore, there is a trade-off. Very small lambda, which means that very small penalty, has the risk of being singular. And you might face a problem of inverting, as in linear regression. Too large lambda reduces your accuracy of regression, because it forgets about your actual cost function. So you need to find the best value for lambda using cross-validation. Okay? So there is a trade-off here. And another thing, we talked about linear algebra. Now let's talk about, in terms of optimization, using this, you are having a penalty on the length of beta. So you don't want beta to become very big vector. Its elements, okay? The length, because a squared L2 norm is a squared length of beta, right? Also, we have some geometrical interpretation at the end of this slide deck, okay? We'll see that. I already have talked about it in the regularization and overfitting lecture. Okay, more general case where P is not necessarily 1. Therefore, labels again can be vectors, right? By the way, if the labels can be matrix too, then it's hard to formulate it because you will have tensors. Okay? Now that labels became vectors, the whole thing became matrix. If your labels are matrix, the whole thing becomes tensor, 3 tensor, 4 tensor. You get it? Okay? You still not, you can do it, but it's hard to write it mathematically. Okay? So minimize B. This again, as you see, the difference here is that you have a squared Frobenius norm of B. Okay? Its simplification, we already had simplified all of these terms. We can write it in this format, trace of that thing transpose itself. Also, this is lambda trace of B transpose B, as before. And again, I'm simplifying it as before. We already talked about it. Here we have lambda trace of B transpose B. Okay, as similar to before. Take derivative, set it to the matrix of zeros, because this derivative is a matrix. Again, the derivatives of these terms we already talked about. The derivative of this term becomes 2 lambda B, because it's quadratic with respect to B. Set it to 0. These two become minus 2x transpose Y. Bring it to the right-hand side. You will have this. You will have this term here. Also this term here, 2 lambda B. Okay, again, factor out 2, scalar 2. Right, factor out matrix B. You will have this in the middle. Again, here, these two 2's cancel each other. This is a pain in the neck. Let's get rid of it by its inverse. You'll have this. By the way, no one asked me in linear regression or even here, there is another way to do this inverse too. So consider the linear regression case. Assume it was singular. So one way in order to handle singularity is regularization like this, ridge regression. Another way is pseudo-inverse. Pseudo-inverse also is a concept in linear algebra you can take a look at. So rather than this inverse, you can take pseudo-inverse if it is singular, and you can't take inverse easily. Okay? Test phase as before. You're minimizing the difference between y and x beta. Therefore, is in test phase, you will have y equals x b. And this x can be either training data or test data with a column of 1 at the start, right? For the sake of bias. So this is x, this is b that we found. Okay. Ridge regression is over. Okay. Now, lasso linear regression. This is a bit harder, but very interesting. Lasso linear regression is L1 norm, regularization of linear regression. First off, let me tell you a bit about L1 norm. I already have talked about it in the other session too. So sparsity is very useful and effective. Just two reasons briefly I mentioned why sparsity is important in machine learning. It can be useful. One thing is that there is a principle in machine learning called betting on sparsity principle. That was proposed by Hasty, Tibshirani et al. At Stanford in the book Elements of Statistical Learning. So what do they say? They say, make me blindfolded. Give me an algorithm which is dense, and also it's sparse version. So it's the same algorithm, dense version, sparse version, okay? Without even looking at the results, I bet that the sparse version will work better. It's not always the case, but it's just betting, okay? Usually that's the case, okay? That's one thing. Another thing which can explain why sparsity is good is Occam's razor in philosophy and logic. Occam was an old, ancient philosopher saying that when two things can explain a phenomenon, the simpler one is the better. An example is that I'm hungry. One reason is that I haven't eaten for hours. Another reason is that an alien made me hungry. Both explain why I'm hungry. The reasonable reason is that I haven't eaten for hours. Okay, so Occam's razor says simpler is better. Okay, so for these two reasons. Now, therefore, when we want to make algorithm sparse, consider X d-dimensional. For having a sparsity, we should use subset selection as the regularization. And it's this. So we call this L0 norm with double quote. Why? Because it's not a norm. It doesn't satisfy the properties of the norm. Recall preliminaries, properties of the norm. Okay, and it's defined as this, equation 18. What is it? Summation of all of the it just counts the number of non-zero elements. So the more zeros you have, the less this L0 norm will become. That's why we are penalizing it. We want it to become close to zero. So we have a lot of zeros. We have few number of non-zero elements, okay? And however, it's not a norm. It's not convex. It's hard to optimize, okay? It's not even smooth. So convex relaxation, let's relax it to a convex function. For the convex relaxation of L0 norm for subset selection is L1 norm. So the closest norm, which is actual norm, to the L0 norm is L1 norm, okay? Which is actually norm and satisfies the properties of the norm. So I can replace that subset selection with L1 norm, okay? L1 norm is convex, it's a norm, but it's not a smooth, but that's fine, that's fine, okay? As I said before, in mathematics, there's always trade-off. Whenever we get something, we lose something. We want to become sparse. We are getting sparsity. We are losing simplicity. It's hard to optimize it. Okay. If you are lazy, you can work with L2 norm. It's not sparse anymore. It works a bit. It's not sparse, but it's easier to work with. Okay. Now, L1 regularization is also referred to as lasso regularization, short for least absolute shrinkage and selection operator. Lasso stands for this. This name was named by Tibshirani. Tibshirani proposed this name, okay, at Stanford. So, yes. Okay, we add L1 norm regularization term. Consider the case where labels are scalar. Okay. Here is the same as before, the cost, actual cost. The regularization term is lambda. What is this? This is definition of L1 norm of beta, vector beta. Recall preliminaries. Okay. A summation of absolute values of elements. Absolute value is not smooth. That's fine. Lambda is a regularization parameter. This denotes the absolute value function. We can write it in matrix form as this. We had it before, so we have lambda L1 norm of beta. Okay. Now, do you remember this X, matrix X? Which was n by d plus 1 dimension. Right? So we had n rows. We were putting them row-wise. But we had one additional column for the bias, once. So it was n by d plus 1 dimensional. Now I'm considering each of its columns. Okay, so let the kth column of X be xk prime. Why do I put prime? I don't want you to confuse it with X. X's were the data which were d-dimensional. Okay, this xk prime is n-dimensional. Why? Every column is n-dimensional, right? We have n rows, d plus 1 columns. Every column is an n-dimensional vector. You can see it as this. So each of these is a column vector, right? Okay. Why am I doing this? Why am I doing it? Because it's L1 norm. There are several ways to optimize for L1 norm regularization, such as proximal operators, such as coordinate descent, such as soft thresholding, these things. I already have talked about all of these methods in my optimization techniques course. You can take a look at that for the session about non-smooth optimization on YouTube channel. So one technique that we can use is coordinate descent. And all of these techniques usually work coordinate-wise. So coordinate descent says that let's consider one coordinate at a time. And the rest, let them be constant. So I don't care about them. I don't optimize with respect to them. Only one coordinate at a time. Its idea is similar to Gibbs sampling. In a statistics, when you do Gibbs sampling, it means that I always sample. I want to sample from a distribution. I sample from the distribution of one of the coordinates conditioned on all of the other ones. So this is the idea of Gibbs sampling in statistics. Similar idea in optimization, coordinate descent. Okay. So why do I have to do it? Because it's non-smooth. L1 norm is not as smooth at origin. Okay. Then so I can write this x beta, right, as this summation, where I'm considering each element of beta k. K goes from 0 to d plus 1, right? K goes 1 or 0. 1. Give me a second. I think it needs to be 0. Yeah, I think I can set it to 0. Sorry about that. Am I right? Yes. Because we also, the first column of x is 1s, right? Sorry about that. This is a type. Okay. So these are beta 0 to beta d plus 1. Okay. See, I have summation of beta k is a scalar now, beta k, the kth element. Xk prime, the kth column of matrix X is a vector n-dimensional. N-dimensional vector. So the whole thing is n-dimensional, some linear combination of n-dimensional vectors. Y is also n-dimensional, right? Right? Also have a squared L2 norm, as here I have. Here I have L1 norm of beta. Now I'm gonna simplify it further. Again, as I said, I want to consider one coordinate at a time and the rest as constant. Therefore, I break this summation to two things. This summation and this. So I take out from the summation, I take out one of the coordinates, let it be beta j. Okay? So do you agree that this summation is beta 0 x 0 prime plus beta 1 x 1 prime until beta d plus 1 x d plus 1 prime. Do you agree that? Okay. One of these elements is, let it be beta j xj prime. Do you agree? One of them. I take it out from this summation and I have the rest of the sum, right? So this is the rest of the sum. As I said, this is exactly like before the previous sum. However, I say k is not equal to j. So all of the elements except the jth one. Okay. Now here is the jth one. So I brought it out of the summation. Why? Because I want to work with beta j. Let's go further. So I'm repeating what we found here. Okay. See, take a look at it here. I define a variable named z, which is n-dimensional, a vector z n-dimensional. I defined it. Why? Because I want to replace this with something. Because the whole thing, y minus this summation, is constant with respect to beta j. So I name it z. You can name it table, whatever you want. Okay? So z, so this becomes this, simplified to this. You will have minimization of this. So this, still consider the fact that still this is beta 1 to beta d plus 1. But when I do coordinate descent, it will be only beta j. So here I have all of the optimization variables. But when I do coordinate descent, I only consider beta j. Okay? So this became this. This is also repeated here. Now, when I do coordinate descent, only I optimize with respect to beta j. Also, this is a regularized cost as before. However, there is a difference. This became simplified to this. Why? Again, let me write it down in this way. What is it? The regularization term. What is it? Lambda, recall the definition of L1 norm in preliminaries. Is j goes from 0 to d plus 1, absolute value of beta j. Do you agree? Do you agree? Again, you can write it as absolute value of beta 0, absolute plus absolute value of beta 1 until absolute value of beta d plus 1. All of them except absolute value of beta j are constant with respect to beta j. You don't need to even consider them in the cost function, right? Derivative, because of this. Beta j plus some constant. Do you care whether you put plus c in the cost or not? No, because its derivative becomes 0. So get rid of that in the cost function. So I'm getting rid of all of these except beta j in the cost. Right? Because I know that derivative would be 0. Also, I know z is a constant with respect to beta j. I also know that. I'm repeating what we had here. So summation of L1 norm. So the L1 norm became simplified to absolute value of beta j because I'm doing coordinate descent. Now, the cost, let's simplify it like before. This is a squared L2 norm. I can write it as it transpose itself. It transpose itself. It's quadratic, right? I'm repeating this also here. Apply this transpose into the parentheses. So you will have Z transpose. Here, beta j is a scalar. It doesn't, the transpose doesn't do anything on it, right? So you'll have beta j again, but xj prime is a vector. So it becomes xj prime transpose. Note that if beta j was a vector, then the order would change. But as it is a scalar, we don't care, okay? We'll have z minus beta j xj prime as well. Let's multiply the terms in the parentheses. So we'll have z transpose z minus beta j, which is a scalar, z transpose xj prime minus beta j xj prime transpose z plus beta j squared. Beta j is a scalar. Beta j times beta j becomes beta j squared. xj prime transpose xj prime. And at the end, we have lambda absolute value of beta j, right? As before. Okay. We also noticed that beta j is a scalar. Let's take derivative, set it to 0, as we did it before. Take derivative with respect to what? Beta j. We are doing coordinate descent with respect to beta j. When we say with respect to beta j, as beta j is scalar, the derivative is a scalar. Why? The whole thing here, the cost is a scalar. So these dot products are all a scalar, right? Derivative of a scalar with respect to a scalar is a scalar. Recall preliminaries. So this first term is constant with respect to beta j, goes away. The second term with respect to beta j becomes this. Beta j is a scalar. Whatever is multiplied to it comes in the derivative. Here also, its derivative is this, right? This third term. The fourth term, beta j squared. It's quadratic, so it becomes 2 beta j, and also what is multiplied to it, right? At the end, the last term, which is lambda absolute value of beta j. What would it be? Its derivative with respect to beta j. Let's plot the absolute value function. It is this, right? What is its derivative? It's exactly the sine function, because this part, its derivative is 1, its slope is 1. This part, its derivative is -1. What is this function? It's a sine function. Wherever x is positive, it's 1. Wherever x is negative, it's -1. It's exactly sine function, sine of x. So derivative of absolute value of beta j becomes sine. Note that you can't do it for L1 norm. You can do it for absolute value. That's why we do coordinate descent, to simplify or reduce L1 norm to absolute value, because we know what the derivative of absolute value is. Okay. Now, so we can do further simplification. We know that z transpose xj prime can be written as xj prime transpose z, because it's a scalar. X transpose y becomes y transpose x, doesn't matter. So you can write it these two, you can write it as -2 xj prime transpose z, right? We also repeat this term here, 2 beta j xj prime transpose xj prime, and also I'm repeating the last term, lambda sine of beta j. Set it to 0, and this 0 is a scalar because the derivative is a scalar. Now, what is it? You tell me. Consider two cases. If beta j is greater than or equal to 0. So the first term, we will have it minus 2 xj transpose xj prime transpose z plus 2 beta j xj prime transpose xj prime plus the third term becomes lambda beta j. When beta j is greater than or equal to 0, sine of beta j becomes beta j. So, sorry, I apologize. Sine of it becomes 1. Right? We'll have only lambda. So sine of it becomes 1. Set it to 0. Rearrange the whole thing. So bring lambda to the other side. It becomes minus lambda. You will have so you will have, let me write this down for you. So you will have 2 beta j xj prime transpose xj prime equals, so I bring this one to the right hand side. It becomes 2 xj prime transpose z minus lambda. I divide the sides by this xj prime transpose xj times 2, okay? Then what would I have? Beta j equals 2 and the 2 here and the 2 here go away, cancel each other. So it becomes xj prime transpose z over xj prime transpose xj prime minus lambda over 2. Am I right? Oh, by the way, I think, sorry about these mistakes. I need to have xj prime transpose xj here too. I apologize. Do you get it? So in the denominator, I'll have xj prime transpose xj. Did you get it? Okay, sorry about this typo, doesn't matter. Did you get the idea? Also, when beta j is less than 0, what happens? The sign of beta j becomes minus 1. So we'll have minus lambda at the left-hand side. When you bring it to the right-hand side, it becomes plus lambda. And then we'll have, after rearranging, you will have plus lambda over 2 xj prime transpose xj. Okay? By the way, I will correct these typos when I upload. Okay? So, did you get it? Now, this is beta j. So, when beta j is greater than or equal to 0, this is the formula for it. When beta j is less than 0, this is the formula for it. So what would you want to find? Beta j. J goes from 0 to d plus 1. So you calculate this for how many times? For j equals 0, j equals 1, until j equals d plus 1. You do it for all of them. Every coordinate at a time. Okay? Now, as I said here, we also have xj transpose xj prime. Here also we have xj prime transpose xj prime. Okay? Consider the fact that, please listen. Consider the fact, do you remember how did we start here? The optimization problem was this: minimize this squared L to norm plus lambda beta j. What if I put 1 over 2 here? Does it matter? The scale in optimization doesn't matter. Whatever you put, the optimization variable adjusts itself, right? To minimize or maximize it. So we don't care. However, why can I put 1 over 2? Because it's becomes simplified. If you put, so here, when we simplified the expression and took derivative, just put 1 over 2 before the norm, and you do the calculation as we did. So you'll have 1 over 2 here, 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 except lambda, right? If you do this, you will see that the 2 goes away in the denominator of lambda. The 2 goes away. These two 2's in the numerator and denominator of the first term already cancel each other. Doesn't matter. But the 2 goes away in the denominator of lambda if you put 1 over 2 before the cost function. Also, I forgot to make it 4 hours. Okay, just give me a sec. Give me a sec. Okay, so what were we saying? We were saying that, so if we have 1/2 before if we have 1/2 before the cost function, then the 2 go away in the denominator of lambda. Also, you should note that if we, so do you remember xj prime? It was the column, jth column of x, right? What if we normalize the columns of x? So their length, the length of each column of x becomes 1. Assume we normalize it. So the first column would be 1/n, because we had 1, 1, 1, 1, 1. I think it would be 1/n or something like that, or 1/n². I should think about it, but it doesn't matter. The length should be 1. So the length of each column should be 1. Okay. If we do that, then xj is then when a squared L2 norm of xj prime becomes 1, right? So because L2 norm of xj prime will be 1, then a square L2 norm of xj will be 1. Then xj prime transpose xj prime becomes 1, right? Then it simplifies the whole equation. The denominators go away. Do you see that? We have xj prime xj prime transpose xj in the denominators. They will go away and we will get simplified as equation 27. Okay? What is this? Let's plot it. For when beta j with respect to xj prime. When beta j is greater than or equal to 0, we have the line xj prime transpose z with the bias minus lambda. So if you continue this, this will be minus lambda. When beta j is less than 0, which is this region, then it will be the line xj prime transpose z plus lambda. If we continue this, it will be plus lambda. So this function, and also the rest will be, beta j will be 0, right? This function is called soft threshold. So as you see, with different approaches, when you solve the lasso regularization, you will end up with soft threshold. Okay, this is the solution of lasso regression. Let's compare them geometrically. An intuition for why L1 norm regularization is sparse is illustrated below. It's credit of Tibshirani in his paper 1996. This is the year in this paper he proposed lasso linear regression that we just learned. 1996. Tibshirani at Stanford. Well, so the objective J has some contour levers like a ball, right? Has some contour levers. So each of these lines, contour levers, means that the function value is the same at that. So consider it's a, why is it like that? Why is it like a ball? Recall the cost, the actual cost. What was it? The actual cost is quadratic, like a ball, right? Quadratic. Here, these are the regularization terms. Let's talk about that. And you will see the beauty. So here, these are the actual costs, which are quadratic. These are the unit balls of the norms, which we are using for regularization. This hypersphere is the hypersphere where it has its interior. So it has its interior. It's the unit ball for L2 norm. Okay. This one, it's like a diamond. Its interior also has its interior. It's it's the unit ball for L1 norm. For more information, see my course optimization techniques, okay? Now, these two should touch each other at some point. So if we didn't have any regularization term, what would we find? The minimum of the both, right? Because we are minimizing that. So this would be the solution. X1 star, X2 star. Without it, so linear regression finds this simple linear regression. But when we have the regularization term, it means that we don't want our beta to become huge, okay? Therefore, we don't here also when beta has become huge, X is also, it seems like X is also huge. So it means that you are going up in the X and Y directions. Here we are showing it in 2D, okay? We want it to be only encapsulated in this norm. I don't want it to explode, okay? That's what regularization does, right? So these two should touch each other. Therefore, where they touch each other is the actual solution. Here, for example, this is the solution of ridge regression. Do you see the difference of ridge regression and linear regression? Here, this is the solution of, you tell me, lasso linear regression. Now, let's see, take a look at that. Here, in ridge regression, one of the coordinates is very small. The other one might not be that much small, although they are both smaller than the solution of linear regression. By the way, I think you can consider this as beta. Sorry about that. I put X1 here. I brought it from another slide of mine. So these are betas. So I don't want betas to explode, okay? Because the solution we want to, the thing which we are optimizing is with respect to beta, right? So beta 1 star, beta 2 star, here is beta 1 dagger, beta 2 dagger. Beta 1 dagger and beta 2 dagger are the solution of ridge regression. Beta 1 star and beta 2 star are the solution of linear regression. We don't want betas to explode. That's why we are doing regularization. And here, beta 1 dagger is a small. Beta 2 dagger is also small. How did it happen? Because of L2 norm regularization. However, here, beta 1 dagger is almost zero, exactly almost zero in this corner. Beta 2 dagger is a small. What does it mean? Beta in lasso regression, beta 1, one of them betas became exactly zero. In L2 norm regularization, they become small, but they never became zero. Exactly what we talked about. Lasso regularization or lasso regression here makes it sparse, makes many of them zero. Now this is in 2D. Consider multi-dimensions. Let D be huge. So here we only have beta 1 and beta 2. Let D be huge. So this in ridge regression, this ball will be like a hypersphere, including its interior. And this diamond will be like I can't visualize it. I need to imagine it like a diamond with a lot of sharp vertices. When you touch one of the in lasso, when you touch one of the vertices, many of the coordinates become zero. Many of the coordinates. However, in ridge regression, many of them become small, not zero. That's the difference geometrically. And Tibshirani had this analysis in his paper. Okay, acknowledgement. For more information on linear regression, take a look at Hastie, Tibshirani, Friedman, and Friedman's book, Elements of Statistical Learning, Data Mining, Inference, and Prediction by Springer, 2009. This is an important book. Another book suitable for sparsity in machine learning is by Tibshirani again, Wainwright and Hastie. These are at Stanford. Statistical Learning with Sparsity. It talks about lasso a lot. The lasso and generalizations in Chapman CRC 2015. Some slides of this slide deck are inspired by teachings of Professor Mujou at the University of Waterloo, Department of Statistics, and Professor Hoda Mohammed Zadeh at Sharif University of Technology, Department of Electrical Engineering, okay? references. This is the book of Boyd, okay, on optimization, which is a good book, but in Cambridge Press, 2004. What is this? This paper by Donohoe, for most large underdetermined systems of linear equations, the minimal L1 norm solution is also the sparsest solution. This is the paper which discusses that the convex relaxation of L0 norm is L1 norm, right? In 2006. This is the paper of Tibshirani in 1996, regression shrinkage, because it's shrinking, right? It's shrinking by regularization. Regression shrinkage and selection. So shrinkage is for L2 norm, selection is for L1 norm. Lasso. Regression shrinkage and selection via the lasso. The paper proposing lasso regression. This is the elements of a statistical learning book. Also, this is the statistical learning with a sparsity book. Okay, let's have a break and come back at maybe 10 to the 9. Okay, 15 minutes. Yeah. Okay, thank you. Okay, so in this course, whenever we explain the theory of the algorithm, so we have a lot of different algorithms that we're gonna cover in different tasks of machine learning, such as regression, classification, dimensional reduction, etc. Okay, each of them I will try to show you some libraries and examples for you to know how to use them in practice too. So as much as I can. So if you search in the internet, sklearn. So sklearn is also pronounced as scikit-learn. Doesn't matter. Scikit-learn or sklearn, regression, linear regression, or scikit-learn ridge regression, scikit-learn lasso regression. It will give you these pages. Okay. Scikit-learn is a library for basic machine learning. Okay, for basic machine learning, and I mean non-deep machine learning. So you can find a lot of algorithms implementation in Python in this library. So as you see here, for example, linear regression. You can also find classifiers, which we are gonna cover. So there is a sklearn linear model linear regression. So sklearn, you can see it as a big library. Inside of it, it has a module linear model. So different linear models, one of which is linear regression. That the simple linear regression which we discussed. Its parameters, so it's a class. And are you aware of object-oriented programming? So object-oriented programming, you have some classes, you make some objects, you call the functions or also call the methods of those objects, and they do something for you. They also have some attributes, and you set the attributes. So here is a class. Its parameters for setting the attributes are these, so the different things. For example, here, some of them I even don't know, but some of them are important. For example, usually n jobs is for how many processor cores do you want to assign to them. Usually people set them to -1, I guess, as far as I remember, meaning that use the most number of cores that you can. But you can leave many of them to be their default unless you want to set some of the parameters to what you want. So for example, fit intercept. Do you see this? The first one, it says, do you want to consider the intercept or bias? Something like that. So it's actually asking whether you want to consider beta 0 or not. Okay. So, and I don't know about the other, you should read about this. It has an explanation of what these are. So there are some other attributes. but let's go down. When you go down, you see some examples and some methods. So first you need to make an object of this class. So as you see here in this line, we import this package or library from sklearn.linear model. From this package, import linear regression. Don't import the whole thing, only linear regression, okay? Import is like include in C, okay? And here we have X equals np.array. So np numpy.array, this is just for the matrices. So matrices and vectors in Python, you need to define them as numpy array. NP stands for numpy. So also you need to import numpy. Import numpy as NP. Okay? You can import numpy, but numpy is large. Therefore, people try to summarize it. They say as NP. Therefore, whenever they say NP, it means numpy. And you will have np.array. And what is this? So we'll have a matrix. The first row is 1 and 1. The second row is 1 and 2. The third row is 2 and 2. The fourth row is 2 and 3. Therefore, it's a 4 by 2 matrix. 4 rows, 2 columns. Okay? And usually in scikit-learn, it gets X and Y. X as data, Y as label. And usually X's are row-wise, stacked row-wise. Okay? Although in calculations, we might, in many algorithms, except this regression, we usually consider samples to be column-wise because we want them to be column vectors. But scikit-learn considers them to be row-wise. Doesn't matter, it's just a convention, okay? So it means that we have here, it means that we have 4 data points, 4 vectors, each of which is 2-dimensional, okay? And also, we have some label. It has generated some fake label defined by some formula, doesn't matter, okay? And then here, reg is the number of object, the name of the object that we want, doesn't matter, you name it table. Reg equals linear regression. So this, here we are calling that class. So the easier way to understand, you can say that linear regression equals reg, then you say reg.fit, okay? But some people do the 2 lines at the same line. They want to do it faster, sooner, I don't know. They are lazy for coding. So they say linear regression, at the same time, they also fit it. Fit in scikit-learn means train. Transform means test phase. You can test the train also. You can test the train data. Doesn't matter. Transform means use the trained model as the test, okay? Whatever you want as input. So fit trains that, transforms that or as a test phase. Also, we usually have fit underscore transform too. It means that fit the model and also transform it. So fit the model and test the training data to fit the model by the training data. Also test the training data. See how it is. So fit underscore transform. So these 3 things, fit, transform. And some algorithms don't have any test phase. They only, for example, some of the dimensionality reduction algorithms, they only reduce the dimensionality of the training data. In other words, they can't handle out of sample data. They can't handle test data. If you go to their libraries in scikit-learn, they don't have any transform function. They only have fit or fit and transform, fit transform. Okay, that's one thing. Also, so when you do this, in this line, you're transforming it, so you're fitting it, so you're trained the model. What does training mean here? It means that beta equals x inverse, x transpose x inverse, x transpose y. This line does that for you. And then reg score, it just calculates the score or accuracy. Here, as it is regression, there is no accuracy. Accuracy is for classification. There are some scores for regression, such as R2 score. You can take a look at them for saying how good the regression is, okay? So it gives you some scores. you can also access the attributes of that object, such as intercept. What is this intercept? It's beta 0. So you can also accept. So what is this coef? Coef is short for coefficients. It gives you the betas. But apparently it gives you beta 1 until beta D. Beta 0 is intercept. Okay, beta 0 is intercept. And also here reg.predict or transform. Here it is called predict. Usually it is called transform in scikit-learn. Apparently in these regression models, they call it predict. Doesn't matter. Predict or transform, you give the data, test data, and gives you the y, the predicted y. What does this line do? If you go into the code, you will see it's doing beta, x beta, x beta. Y was x beta, right? This is exactly it's doing. So fit here, fit, where was that? Here, fit calculates beta using that formula that we derived. Predict says x beta for the input x, right? Okay, this is what it is. And this is linear regression. We have ridge regression. Another package, ridge regression, which does the ridge regression. Here it is. Some examples is, again, it's a class. We make an object. You can also set the random state. Sometimes when you want to generate random data or something, when you set the random seed, whenever you run it, it gives you the same thing, the same random number. So you do it because you want it to be replicable, something like that. You repeat it for several times. And then rand n gives you Gaussian data. Rand n is short for rand normal, random normal distribution. Ridge is you are just making an object of ridge class, ridge regression, which is L2 regularized linear regression, right? Usually in scikit-learn, people call it CLF or reg. Reg usually stands for regression, whatever. CLF is short for classifier. Here, I think by mistake, they made it CLF. You do reg. Doesn't matter, it's name. You can call it table. Table equals ridge, right? But CLF is usually used short for classifier, although here it's not classifier. Doesn't matter. It's just naming. Then so CLF is the name of object. You can call it Benjamin. Benjamin.fit or CLF.fit, X and Y. Y, you need both X data and Y as label for training. Reach Y. Yes, sure. So here, as I said here, we make, what do we do here? We make we import the library, also the NumPy library. We generate some data. Here we generate some random data. Here we make an object of reach with some parameters. What is alpha here? Lambda in our slides, the regularization parameter. You can tune it by cross-validation. Here you do fit, training, and then you can also do transform or predict, okay? This was reach, so let me zoom also for the linear regression. This was linear regression, which we discussed. Here coefficient is betas, gives you betas, intercept gives you beta 0. You can also have here fit for training, predict or transform for testing. So we talked about it, and now the lasso. Lasso is L1 non-regularized regression. You can take a look. It usually gives you some examples like this. Also, the methods are explained below. Fit. For example, here you don't know whether X is row-wise or column-wise. It tells you. See, X is an NP array, ND array means that NumPy array, but it's D array. It means that it is multiple dimensions. It's not one vector. It's matrix. Okay, and its size is n samples by n features. It means that it's n by d, not d by n. Therefore, the vectors are put row-wise, right? N samples is number of samples. And n features means number of dimensions, features. N stands for number. And Y also is a vector or a matrix. It also takes care that maybe P is greater than 1. Maybe labels are vectors. So N samples, N targets. And N targets is P in our slides. N features is D in our slides. Right? So here it is. And then some example from scikit-learn or scikit-learn import linear model. Linear model dot lasso. You set alpha here is lambda in our slides. You fit, this is the input data, training data, you fit it, and then you can also see the coefficients, intercept, you can also transform or predict. So we saw some examples, for example, you can run, you have some points, you fit a line to these points. And as you see here, it's 2D. So X is one-dimensional here in this example. Data is one, and label is also one-dimensional. So you can plot Y versus X. And this is so what does it mean? What does this line mean? It means that for this X, for example, the cursor is showing, for this X, it predicts this Y. So although, for example, in actual, Y might be here that I'm showing, but what I predict is here. The error is small. The error could be worse. It's after optimization, right? Of course, if you regularize it by ridge or these things, it would be better. Now I think you see, if the data, the pattern of data is not linear, linear regression would not be good. Example, here. This data is not linear. If you apply linear regression, it will fit a line like this. It would not be perfect. Of course, if you use nonlinear regression, such as neural networks and these things, it would be better for nonlinear pattern. However, for linear data, let me bring it. For linear data, it's almost working well, right? And here it is Y versus X. Y is one-dimensional, X is one-dimensional, P and D are one. But if P and D are huge, then you can't visualize it. You need to imagine it. So, and this line will be a hyperplane, right? So, okay, this is an example of what we talked about in coding and these things. So let's go to next topic. Now that we saw regression, linear regression, let's go to classifiers to start classification. Okay, one of the simplest classification methods is linear discriminant analysis, and also its counterpart is similar algorithm is quadratic discriminant analysis. Okay, these two algorithms also have their package in scikit-learn. So you can find LDA and QDA in scikit-learn too. So linear discriminant analysis and quadratic discriminant analysis. Optimization for the boundary of classes. Okay. So assume we have a data set of instances xi and yi. Okay, I goes from 1 to n. Again, we have pairs of data and labels. Okay, here labels are scalar. Why? Because we have classes, class 1, class 2, class 3, right? It's not regression anymore. With sample size n, dimensionality, xi's are d-dimensional and labels are scalar. The yi's are class labels, okay? We would like to classify the space of data using these instances. In other words, what LDA and QDA do, they partition the space. For example, these are my classes. What do? They partition the whole space into this star class and circle class. They partition the space. This is LDA, QDA is quadratic. It's not linear. The decision boundary is quadratic. For example, QDA will be like this. So this is what LDA and QDA do. They partition the space. Okay? They classify the space of data using these instances. Now, for example, a test sample comes here. The LDA would say it's a star class. Okay? So linear discriminant analysis, or LDA, and quadratic discriminant analysis, QDA, are two well-known supervised classification methods. Supervised because they use labels. They have a probabilistic approach. Okay, they have a probabilistic approach. First, suppose the data is one-dimensional for simplicity. Okay. Then we assume that we have two classes with CDF. What was CDF? Cumulative distribution function. Recall preliminaries. It integrates or sums the probability PDF until, or PMF until some point. F1x and F2x, I show them like capital CDF, okay, respectively. Now that the PDF, probability density function of these be this. So PDF is the derivative of CDF. We talked about PDF and CDF in preliminaries, okay? We assume that these two classes have normal distribution. So this is the assumption of LDA and QDA, that the classes, the distribution of classes is Gaussian, okay? This is an assumption that they make. Why is it valid assumption almost? Because this is the most common distribution in the nature, in the world. Even the filters in our eyes have some Gaussian distribution, okay? So this is the nature. But of course, we might have some classes which don't have Gaussian distribution, and LDA and QDA would work very badly on them, right? So in order for them to work well, the distribution should be actually Gaussian, almost. So this is the most common and default distribution in the real world application. The mean of one of these two classes is greater than the other one. Do you agree? So when we have two classes and they are one-dimensional, it's one-dimensional. One of the means is here, maybe one of the means is the other one, right? So mu1, mu2, one of them is less than the other one. It's one-dimensional. If it was multi-dimensional, you couldn't say, it doesn't make any sense. But it's one-dimensional. Okay. The mean of one of these two classes is greater than the other one. We assume that mu1 is less than mu2, right? The mean of the classes, the average of the classes, mean of the class. An instance X belongs to one of these two classes, okay? If X, data point X, and X here is a scalar, for now assume it's a scalar, is in class 1, C1, its distribution is normal Gaussian distribution with mu1, sigma 1 squared. If it's in class 2, its distribution is mu2, sigma 2 squared. Mu's are the means of the distributions, sigma squareds are the variances of the distribution. For an instance X or data X, we may have an error in estimation. So what does it mean? At a point which we denote by X star, the probability of the two classes are equal. For example, this is one of the distribution of the first class. This is a distribution of the second class. When the point where they interact, the probability is the same. Here, the probability of the two of them is the same, right? For example, here, the probability of second class is higher than the probability of the first class. Here, at this point, the probability of the first class is higher than the second class. At this point, the probability of the two classes is the same. Let this point be X star. LDA finds this x star and sets it as the decision boundary for the two classes. Okay, exactly where the probability of the two classes is the same, equal. This is where LDA puts as decision boundary. So here, above x star here, if we say it's in class 1, it is an error. Because it sees the probability of class 2 is higher. Below x star, if we say the point x is in class 2, it's error because the probability of class 1 is higher. Okay? What is the probability of error then? If x is in the class 1, but if x is greater than x star, but we say it's in class 1. Plus the probability that x is less than x star, but we say it's in class 2. This is the probability of error, right? Do you remember this? Recall preliminaries. The joint probability of A and B, you can write it as probability of A given B times P of B. Therefore, I can write this term as this: P of x greater than x star given x belonging to C1 times P x belongs to C1. Also, this term, you can write it in this way: P of x less than x star given x belongs to C2, P of x belongs to C2. Okay, we want to minimize this error with respect to this x star. So we want to find which x star is good, and we will end up saying that x star is where the probabilities are equal. We will end up with it, okay? And this x star is the decision boundary. Okay, so I'm repeating what we had, P of error. Now, according to the CDF, definition of CDF, cumulative distribution function, what is it? P of x less than C and P x being in the class 1 is F1C. So why F1? Because it is in class 1. And why CDF? Because it's less than C, right? Also, F2 is probability of x less than x star and x belongs to C2. Why F2? Because x belongs to C2. And why, by the way, x star here? Because x is less than x star. Why was here C? Because x was less than C. Okay. Now I have this. Can I write? Now consider this. Can I write P of x greater than x star? X belongs to C1 as 1 minus F1 x star. Okay, let me talk about it. F1 x star is P of x less than x star and x belongs to C1. Agreed? Agreed? Do you agree with this? Okay, then what is P of x greater than an x star and x belongs to C1? It's 1 minus P of x less than x star and x belongs to C1. Right? Now replace this with F1 x star that we just talked. You will get equation 7. Okay? Now let these are called priors. Prior of class 1, prior probability of class 2. Okay? Let them be denoted by pi 1 and pi 2. You can write it as F1x and F2x, which are the PDFs of class 1 and class 2. Okay? Probability density functions of class 1 and class 2. Okay? Now, put all of these notations in the probability of error that we had. So here, what was that? We just talked about it here. It's 1 minus F1 x star. This is prior of class 1, pi 1. This, we just talked about it here. This is F2 x star. This is prior of class 2, pi 2. So I'm restating this probability of error in equation 11. I'm also minimizing this probability of error, right? Because I want to have less error, right? Now what is it? Now, okay. We take derivative, set it to 0. It's an unconstrained optimization problem because of first order optimality condition. Take derivative, set it to 0. Our optimization variable is x star. So what is its derivative? This 1 is constant, it goes away. So we have minus here. The derivative of CDF is PDF. Pi 1 is constant, multiplied. Here, the derivative of CDF is PDF, F2 x's. Pi 2 is constant, is here. Set it to 0, rearrange. So bring this to the other side. You will have this. F1 x star pi 1 equals F2 x star pi 2. Another way to find that equation is this. Another way, approach 2, is that we want to equate the posterior probabilities. Again, as I said, LDA and QDA say that the posteriors, I want them to be equal, the decision boundary. Okay, so what is the posterior? Posterior is this. Given data, the probability of label given data. Okay, probability of label 1 given data, set it to equal to probability of label 2 given data. So I want to see where these two Gaussian distributions are equal. Now, according to Bayes' rule, recall preliminaries. According to the Bayes' rule, I can write it in this way. Probability of data given label C1 times prior of C1 over probability of data, prior of data. So I can rename them as we had F1x and pi 1 here. Also this, what is this? Probability of data given x belonging to the class CK prior of CK. So what I'm doing is that I'm saying that P of x given x belongs to CK times P of x belongs to CK. And I'm summing over all of the classes. This is called marginalization. These are terminologies in probability. I'm marginalizing over all of the classes. So the effect of classes goes away by this marginalization. Okay? So now, this is likewise, I will have probability of x belongs to C2 given data. I set them equal to each other. And these two go away, the denominators. I will get this as before. Okay? This is the equation for the LDA and QDA. Now let's derive them using those equations. Now assume that the distribution of the data is multidimensional. So far we assume that the data is scalar for the sake of simplicity in derivation. Now assume data is multidimensional, d-dimensional, and it has Gaussian distribution. So X has mean mu and covariance matrix sigma. Okay? Why do I make this assumption? This is the assumption of LDA and QD. This is a PDF formula for PDF of Gaussian distribution. So this is the normalization factor. This pi, don't confuse this pi with pi 1 and pi 2. Pi 1 and pi 2 were the priors of the class 1 and class 2. This pi is 3.14. Okay? This is the determinant, determinant of covariance matrix. Also, this is inverse of covariance matrix, x minus the mean. Okay? And this is exponential operator. Okay. And now recall what we had in equation 15 or equation 12. Okay? Let's replace F1 and F2 by the Gaussian distribution. So you will have equation 17. So this is the Gaussian distribution of, this is F1, pi 1, F2, pi 2. Okay? Now LDA starts. In LDA, we make another assumption too. So one of the assumptions we made was the distribution of classes. Another assumption we make is that the covariances of the two classes are equal. Okay, so sigma 1 and sigma 2 are equal to each other. Let's name them sigma. Okay, so I replace sigma 1 with sigma and sigma 2 with sigma. Okay, in the equation 17 that I had. Now, do you agree that these two cancel each other? These two normalization factors cancel each other. So I will have this. I will end up with this exponential term, pi 1, exponential term, pi 2. Now let's take logarithm, natural logarithm from the sides. So this exponential exp operator goes away. Also, we know that log of AB is log of A plus log of B. Therefore, we have times here, it becomes plus. Also here. So exponential goes away, but here we'll have ln or natural logarithm of pi 1. Also, exponential goes away for this. And also we had pi 2, but we will have log of pi 2. Okay? Plus log of pi 2. Okay, now we can consider this term that we also are seeing here. Take a look at it. Do you see this term? This term. I want to simplify it. Let's simplify it. Here. So I have transpose here. I applied in the parentheses. I'll have X transpose minus mu 1 transpose. Okay. Now I will multiply the terms together. So I will multiply this times this, right? If you multiply the terms, you will have these terms. Do you get it? Okay. Now, you should consider that these two are equal to each other. Why? Because they are scalars. And when it is, the whole thing is a scalar, a scalar is equal to its transpose. So you can transpose this scalar, get this. So they are equal to each other. Therefore, I can write minus 2 of one of them. And I'm repeating the other two terms. I put in the other two terms. Okay? Now, by the way, when I was transposing these two terms, one of these two terms to be equal to the other one, I have sigma inverse transpose. But sigma inverse transpose equals sigma inverse because sigma is diagonal. Sigma inverse is also diagonal. In linear algebra, when we have a diagonal matrix, its diagonal can be proved to be its inverse can be proved to be the inverse of its elements. It's still diagonal. So its transpose is the same. Okay? Now, so I have this. Let's put equation 19. Also, I can do this for this also, the right-hand side. I replace these two terms, the star terms, with equation 19. I will put equation 19 in this equation. So I will have this. I also had log of pi 1 equals this plus log of pi 2. Okay? Interestingly, it simplifies a lot. See, I bring this to the other side, this log of pi 1. So, by the way, I multiply both sides by 2. And then I bring this log log of pi 1 to the right-hand side, I will have 2 log of pi 2 over pi 1. Why? Because log of pi 2 over pi 1 equals log of pi 2 minus log of pi 1. Okay. Also, I can left factor out minus mu 1 transpose and mu 2 transpose, and right factor out mu 1 and mu 2. So here we have mu 1, mu 2. Here we have mu 1 transpose, mu 2 transpose. So I can left factor out mu transposes and right factor out mu's. In the middle, I have sigma inverse. In the middle, I have sigma inverse. So I will have this term. Also, in these two terms, these two terms cancel each other, interestingly. Give me a second. So here, these two terms are left. Again, I left factor out mu 1 transpose and mu 2 transpose. Okay. So I will have mu 1 plus or minus, sorry, because I bring one of them to the other side. Doesn't matter. Mu 1 minus mu 2 transpose sigma inverse x. I'm talking about these two terms. Okay. And then I can restate this as this. Why? Because when you apply transpose to the parentheses, it changes the order. So it will be mu 2 or mu, here it is 2. Mu 2 minus mu 1 transpose, sigma inverse transpose equals sigma inverse. So it will be the same. And as I am multiplying all sides by 2, I'll have 2 here. So as you saw, I simplified this. I rearranged that to get equation 20. Now, with respect to x, see equation 20. With respect to x, is it linear, quadratic? What is it? It's linear. The first term is some scalar, so some vector transpose x, that A transpose x here. Assume this be A transpose. The whole thing here is also a scalar, B. It's like A transpose x plus B equals 0. It means it's an equation of a line. That's why in LDA, decision boundary is linear. This is decision boundary. You see that? Therefore, if we consider Gaussian distributions for the two classes, where the covariance matrices are assumed to be equal, the decision boundary of classification is a line. Because of linearity of the decision boundary, which discriminates the two classes, this method is called linear discriminant analysis. So linear is because its decision boundary is linear. Discriminant in the name is because it's discriminating the two classes. By the way, LDA is short for two algorithms in machine learning. One of them is linear discriminant analysis. The other one is, what was that? I just forgot it. Just give me a second to search it. Latent Dirichlet allocation. Sorry about that, I forgot. So one of them is linear discriminant analysis. One of them is latent Dirichlet allocation. By the way, scikit-learn previously, scikit-learn.lda was linear discriminant analysis. I updated that. Now scikit-learn.lda is latent Dirichlet allocation. And LDA in scikit-learn is scikit-learn.linear discriminant analysis. Okay, it shouldn't confuse these two. Now let's go continue. So for obtaining equation 20, we brought the expressions to the right side, which was corresponding to the second class. Okay. Therefore, if we use some function delta x mapping from RD to R as the left-hand side expression of equation 20, we'll have this. So see, Consider equation 20. Something is equal to 0, right? The left-hand side equals 0. Now let's define the left-hand side to be delta x. Why am I doing this? You will see. Delta x equals the left-hand side. Now the class of an instance x, I want to show you the test phase of LDA. The class of an instance comes x. The class will be if delta x is less than 1, it's class 1. If it's greater than 1, it's class 2. What does it mean? Less than equation of a line, or greater than equation. Less than equation of a line means below the line. Greater than equation of a line means above the line. So these are the two classes, right? So if you set delta to 0, it gives you the decision boundary. But you can feed x to delta to see the class of you need to take the sign of delta. Then it gives you the class of the x, right? Okay. If the priors of the two classes are equal, meaning that if pi1 equals pi2, here we have pi1 and pi2, right? Then this goes away. Why? Because log of 1 is 0. Exact. This goes away and becomes more simplified. It still has intercept, but its intercept is simpler. Okay? LDA is over. So simple. QDA. In quadratic discriminant analysis, very similar to LDA. We just don't make this assumption. We don't assume that the covariance matrices are equal. When we remove this assumption, the decision boundary becomes quadratic. We'll see that. It's not linear anymore. So what did we have in equation 17? We had this. Now we have sigma 1 inverse, sigma 2 inverse. We don't have sigmas anymore. Okay, take logarithm from the sides. Note that now we can't simplify these normalization factors. However, we can handle them. Take logarithm from the sides. So this is the logarithm of the normalization factor. Why? Because logarithm of 1 over a becomes minus logarithm of a. Also, we know that logarithm of multiplication becomes summation of logarithms. Therefore, you will have this. This minus d over 2 is because of this. Because of this, okay? And d is here, and over 2 is because of the square root that we have here, right? And we have log of 2 pi. 2 pi is because of here. Here we also have log of determinant of covariance 1, sigma 1. Again, likewise, we have it for the right-hand side. And the other parts are like before. We are just taking logarithm from the sides, right? Natural logarithm. Recall equation 19. What? So I'm repeating it here. Okay, we simplified that. Do you remember equation 19? We had this term, we simplified it. I'm gonna use the same simplification here. Okay, so I'm gonna replace this and this with their simplifications. By the way, before that, do you agree that these two terms go away? But these two terms don't go away. We have them. So I replace those with the simplifications, and I will get this. So this equation got simplified to this equation. Now multiply the sides of equation by 2. These 1/2's go away, but some of them will have 2. And again, write like what I said before. Left factor out, right factor out terms. Okay? You will come up with this. Do you get my point? For example, consider, let me go very fast with them. So consider these two. It becomes this. Consider these two becomes this. Consider these two becomes this. Consider these two terms becomes this. So I'm bringing one of them to the other side, right? Consider these two terms becomes this. Now, interesting thing happens. See equation 25. With respect to x, is it linear, quadratic, what? It's quadratic. This term, the first term is quadratic. So it's like x transpose AX, where A is the matrix. A is sigma 1 minus sigma 2 is the inverse. And we also have this. It's like B transpose X. But also the whole other thing is a constant, and it's actually a scalar. Mu1 transpose sigma inverse mu1 is a scalar. These are scalars. So plus C. This is quadratic form. Interestingly, in quadratic form, we usually like A to be either positive semi-definite or negative semi-definite. If it is positive semi-definite, meaning that its eigenvalues are non-negative, it's facing up. If it's negative semi-definite, it's facing down. Interestingly, what we named as A is covariance minus covariance inverse. So it's positive semi-definite, right? So for obtaining, again, like before, I named the left-hand side as delta. Left-hand side as delta x. I want to use it in the test phase. I feed data x to it. I take the sign. If it's, now what does this mean? If it's above the quadratic function, it's in one of the classes. If it's below the quadratic function, like this. If it's above here, if it's here in one of the classes. If it's below the quadratic function, is in the other class. If the priors, again, are set to each other, equal to each other, pi1 equals pi2, then this goes away and it gets simplified. I think it's a good point to stop, and we'll continue this in the next session. Okay, thank you.